Air Monitor has prepared today's webinar. Yes, you can accurately measure outdoor airflow. Today's presenters are Barry Dunham and Matt Maragos. Barry is the Director of HVAC Market Development for ONICON Incorporated and Air Monitor Corporation. His design experience includes mechanical, electrical, and energy engineering. Some past projects have involved a wide range of scope and multidiscipline engineering systems such as chillers, cooling towers, energy management systems, and thermal energy storage and data centers. Responsibilities also include compliance with LEED and AMCO-related efforts. Matt is the General Manager of Air Monitor Corporation. Matt has over 16 years of experience providing accurate measurement solutions for challenging airflow applications, ranging from critical utility boiler control to outside air measurement for commercial buildings. In his free time, Matt likes to design and fabricate components for performance vehicles. He graduated from the University of North Dakota with a degree in mechanical engineering. And now we turn the webinar over to Barry. Thank you very much.
Well, thank you. Hello, everyone. This is Barry Dunham with Air Monitor. First off, I want to thank everyone for sharing your time with us today. We're going to discuss airflow measurement in the HVAC industry, specifically targeted towards the measurement of outdoor airflow. One housekeeping note, we will answer all of your questions today at the end of the presentation, time allowing. Anything we don't get to today will be answered via email within the next few days. So again, the topic of this specific webinar is going to be on airflow measurement, and our focus is going to be on outdoor airflow. So just to kind of start right off, the ability to accurately and reliably measure airflow is key in the design and operation of high-performance buildings. It's used to ensure that ventilation code requirements are met. The energy savings initiatives and just energy savings in general are met, and that the indoor environment that's required in design is being provided for in terms of occupant comfort and safety. Our message today is that accurately measuring that airflow can create a challenge. Systems today are difficult to measure due to the dynamic behavior of the airflow and the large variations in the systems that are employed out there. So today we're going to talk about some of the challenges with outdoor air and some of the technologies used to measure this particular challenging application. So why measure outdoor airflow? Unlike other building utilities, outdoor air is basically mandated by code. The code requirements require certain amounts of outdoor air to be delivered to the space. The penalty associated with not measuring outdoor air accurately, they manifest themselves in many ways. We're talking about higher operating costs for the building if we bring in outdoor air, too much outdoor air, uncomfortable working conditions, and there's an increased liability with a building that is underperforming or presents a health issue by not meeting the necessary ventilation requirements. So ASHRAE, they publish a number of documents and standards. Some of the standards are specifically targeted at outdoor air and ventilation rates. Others are designed at how to design and build a high-performance building. And there's other standards that are specifically targeted at meeting energy performance requirements or setting minimum energy standards. So let's talk about ASHRAE 62.1 to start. ASHRAE 62.1 is the standard for the amount of outdoor air or dilution air that needs to be brought into a building based on the building type and the occupancy. The standard also provides guidance in how to balance the need for outdoor air versus the cost associated with conditioning it. Demand control ventilation, for instance, is a means of making sure the right ventilations are met, but we don't want to pay too much of an extreme penalty if that much outdoor air is not required in terms of the energy it costs to condition it. So that alone will create a pretty big challenge in airflow measurement just because of the dynamic range of the different airflow rates and systems that need to be measured. It's interesting to note that ASHRAE 62.1 does not mandate airflow measurement directly, but the direct measurement of the outdoor airflow is the best way to make sure that we're in compliance with the code. And ASHRAE 62.1 has become the de facto standard for most code organizations in terms of the amount of ventilation air required for a commercial building. ASHRAE 189 is a little bit different in that it is a standard for the design and basically the design of high-performance green buildings. ASHRAE 189 goes a little bit further. It incorporates 62.1 in terms of the requirements that are needed for ventilation air, but it also mandates that airflow measurement be made at the system level at each device. It mandates that the airflow must be monitored, and then it goes an additional step, and it mandates the accuracy of that measurement, and that's very important. Mandating the monitoring of an outdoor air measurement is one thing. Making sure that it meets the accuracy requirements is something else. So 189.1 is a very good standard in terms of defining how a high-performance building should be designed and operated. And then ASHRAE 90.1. The minimum energy standard. This standard, it does not mandate or discuss outdoor air directly. However, the systems that it dictates, or the systems that are required based on climate zone, building type, and size, and so forth, will have certain outdoor air measuring challenges associated with them. So the systems I'm referring to are things like economizer mode systems that are mandated, or energy recovery systems. These all impact the amount of outdoor air that's coming into the building, how that is controlled and operated. So that's very important, to meet the requirements of these standards to have accurate measurement. So I want to go through a couple quick formulas and terms just as we get further into the discussion. One of the things that we always talk about is airflow velocity as the measuring point. As the manufacturer, that's really what we're measuring. We're measuring the airflow velocity, what's measured in feet per minute. What's used in the industry is the actual volumetric flow rate. That is the velocity in feet per minute times the duct area or inlet area or whatever it is in square feet. That gives us our volumetric measurement, or cubic feet per minute. It is important to note, though, that the majority of instruments are measuring velocity, and then they are using an area to calculate basically the CFM. And the CFM is really the most important part in terms of design. That's what most building designs are based on, how much CFM a space needs and so forth. So accurate velocity measurement is key in determining accurate volumetric flow measurement. And then the last item, more or less formula I put on there is a pretty basic formula, and I put it here just to indicate, we're really talking about the energy in the airstream. That energy is the equation for that, and this is sensible energy only. It's a pretty simplistic equation at this point. Your CFM times a constant times your differential temperature defines the amount of energy in that airstream. And for outdoor air, what we really need to be aware of is that delta T and that CFM. That's what requires the energy that we have to either impart on the airstream coming in. If it's very cold air, we've got to heat it up to the building temperature, or if it's extremely warm air, we've got to cool it down. So having an accurate measurement of that CFM obviously will allow us to operate more efficiently in terms of the amount of energy it takes to condition that ventilation air. Another term that we have to discuss when we're talking about airflow measurements or compressed fluids in general, we have to express them in either actual or standard conditions. Standard conditions are basically a volumetric condition of a compressible fluid at a standard 70 degrees or thereabout 70 degrees and atmospheric conditions of 14.69 psi. Actual conditions in the HVAC industry are pretty much standard conditions for most applications. Most of the time we're around 70 degrees, and if you're at sea level, the pressure in your ducted systems are right around atmospheric or the pressure associated with sea level. So it's a straight, most of the time we don't do any compensation, or we may not do compensation in terms of the different airstreams coming together and being mixed within the system. Now, when does a standard volumetric airflow rate come into play? When is that required? Well, the answer is anytime you're operating above sea level or at temperatures significantly different than 70 degrees, we need to be able to compensate that measurement. And we have to compensate that measurement really for the air density associated with it. That airflow density change, number one, it affects the measurement itself because it will affect the velocity pressure measurement of the airflow. And we also have to make sure that we compensate it for volumetric conditions. In other words, when you're bringing in extremely cold outdoor air and you have to heat that air up, the volume difference, the volume change can be substantial. You know, when you're down around 30 degrees outdoor air and trying to raise that temperature up to 70, you'll have a pretty good 20 to 30% increase in volumetric flow that needs to be accounted for. So for outdoor air measurement, unlike a typical, a supplier return where the temperatures are close together, compensating that flow rate becomes important. Some other terms in that need to be addressed are really, and this comes from a selection basis for us. We see these two terms sometimes interchanged, is face area versus free area. A face area of a duct or inlet is the actual area of that inlet in terms of width times height. It's the total area of the opening. Free area is the face area minus the obstruction in it, such as a louver or screening or something like that. Free area is commonly expressed as a percentage of the face area. And where we see free area discussed is free area in terms of a louver with a free area velocity. So it's just important to note what velocity we're looking at, free area versus face area. And as in terms of pressure, we'll talk a little bit later on about measuring the actual velocity pressure of a system, but it's important to note that all the pressures that are important in doing an accurate velocity measurement in a duct are going to be your static pressure, your velocity pressure, and your total pressure. Now, the static pressure is basically the pressure that acts perpendicular to the duct's walls. It exists all the time within a ducted pressurized system. Velocity pressure is that pressure associated with the kinetic energy of the flow stream. So air moving will generate a velocity pressure. The total pressure is the combination of both static and velocity pressure. Accuracy and repeatability. These are two terms that sound pretty straightforward, but a lot of times they are displaced for one another. Accuracy is the ability of an instrument to provide a measurement as compared to a standard. Repeatability is the instrument's ability to repeat the same measurement when it sees the same conditions. And where this becomes important for airflow, in terms of control, repeatability of a measurement may be more important than accuracy. However, when we're talking about the amount of air being delivered to a space or the energy associated with it, absolute accuracy becomes very important. A couple other definitions that you'll see in measurement systems are turn down and effective turn down. So turn down is quite simply the maximum flow divided by the minimum flow. It's usually specified by an instrument manufacturer for any instrument, not just airflow, but it really just defines the flow range the instrument will operate over. Effective turn down is really the important part of this discussion. The effective turn down is the turn down based on where the instrument will actually operate. So in a real quick example, if you take a flow meter that will measure from 1,500 feet per minute to 150, that's a 10-to-1 turn down, 1,500 divided by 150. If they will never operate in the system above 600 feet per minute, 600 divided by 150 is 4-to-1. So the effective turn down can be much less than the actual turn down. Something that's important to consider when comparing technologies. When you're defining an accuracy statement, there are a couple items within that accuracy statement that we need to address. In other words, we need to have at least 3 things for a valid accuracy statement. We need to have the percent of error or deviation from the standard, and the reference, the percent of what? Reading, rate, full scale, so forth. And we also need to have that range or effective turn down over which it's applied. So, you know, in just terms of reading those accuracy statements, it sounds, you know, pretty straightforward. Percent of reading, you know, that's almost a straight line. It's always the same error associated with the measurement at the point of measurement. Percent of full scale is a fixed uncertainty that is spread across the entire flow range. So graphically speaking, it's a little bit easier to see. What this graph just shows is two different accuracy statements. The trumpet shape is a percent of full scale reading. So what happens is we've got an accuracy statement that says plus or minus 3% of full scale from 150 to 1,500 feet per minute. That means that at 1,500 feet per minute, it is plus or minus 3%, but only at that point. As you pull that measurement back to 150 feet per minute, you'll see that you're plus or minus 30% of the actual reading at that point, versus the accuracy statement that says plus or minus 3% of reading is a straight line. It is always the same amount of uncertainty at that point of measurement. So the important thing to consider here is that percentage of reading at the point of measurement is what we want to account for. We want to make sure that our system is most accurate at that point. So really, it's about, if you want to measure it accurately. That's kind of the measurement, or kind of the message here. And just as a real quick reference, you know, I've had discussions where not all the components of airflow are to be measured. You know, there was a discussion at one point where somebody wanted to do subtraction and says, well, I'll measure supply and return. I will do an assumptive measurement on outdoor air. If I know supply and return, I know outdoor air. ASHRAE, in terms of test and balance, allows, you know, a 5 to 10% uncertainty in terms of test and balance. So let's say you do have a 10,000 CFM system. The balancer would come out, balances it to 10,000 CFM. It's really 10,500, plus or minus 5%. They balance the return at 8,000, but it's 5% low, 7,600 CFM. Not a big deal, right? Except the outdoor air measurement now using subtraction is 2,900 CFM as opposed to 2,000. So we have a 45% error in the outdoor airflow. Depending on the size of the system, the energy involved, the location, that can equate to a pretty heavy penalty in terms of performance. So the next thing to consider in terms of accuracy and airflow measurement is, where are we going to make the measurement? In most systems, a ducted system, the duct is going to be the best place to make the measurement. Airflow, you know, is extremely dynamic. The velocity profiles change. Accurate measurement depends on multiple measurement points. So if we have a duct and we have the ability to input multiple measurement points of that duct, and we have the straight run or the conditioning required, we can get a very accurate measurement. The truth is that in most systems, we do not have the straight run of duct required. And what this shows, this 3D graph, is basically indicating that I've got, at the same traverse point in the ducted system, at two different velocity points, I have substantially different flow profiles. Having more points and measuring at more points is the only way to get an average airflow measurement at that point when we're inside a duct. So everybody you know, publishes minimum installation requirements. And those minimum installation requirements assume ducted or some type of obstruction that we can accommodate for. So if you have duct and you have an elbow or you have a takeoff, the duct itself acts as the conditioner. The friction of the duct wall with the airflow stream over a certain distance is going to provide the necessary profiling to get an accurate measurement. Unfortunately, in some of the installations that we're going to talk about with outdoor air, ducted is you know, an exception, not the rule. So what we really have now is we have systems that are operating in very complex control schemes out there. There are a lot of different installations even within the same system in terms of ducted inlets, non-ducted inlets, that type of thing. So the next section that we're going to talk about is, and Matt's going to address, what are the most common technologies that we have in the HVAC market space, and which, you know, basically, and which is the correct one, and how do you choose the right tool for the job? So without further ado, I turn it over to Matt at this point.
Thanks, Barry. I hope everybody's having a great day. I'm Matt Maragos. What Barry's given us is, a great rundown on why accurate outdoor air measurements are required. Now what we're tasked with is how to do it. How to achieve accurate outdoor air measurement. There's many different instruments and technologies on the marketplace. All of them have their own merit. But the common problem is misapplication of those available technologies, and the results can be very poor on outdoor air measurement. So it's imperative to select a technology that addresses all the unique challenges that are encountered. I'm going to start with the two most common technologies that we find in HVAC airflow today, and those are differential pressure and thermal dispersion. Differential pressure has been around for many, many years. It's considered the standard of airflow measurement. It's a recommended airflow measurement traverse method in the ASHRAE Fundamentals Handbook, and it's widely accepted throughout many industries. It's a direct measurement of the actual components of airflow that Barry spoke of earlier, the total pressure and the static pressure in the duct. DP has a really distinct advantage in that you can have many measurement points. It has the highest density of measurement points of any technology available. And it meets all the ASHRAE requirements regardless of the duct size. So we look up a little bit at the formula. We're going to take the total pressure, subtract the static pressure, and that gets us to the velocity pressure. Since it's a square root function, we're going to take a square root of the velocity pressure, multiply it by 4005, and that gets us to the velocity. Most of the instruments are measuring velocity, and Pitot is no different. From that point, you can apply your duct area and get to volumetric flow. Why 4005 in this case? Because as Barry spoke about earlier, most of the HVAC systems work at standard conditions, 70 degrees Fahrenheit and 29.921 inches of mercury. That gets us to that 4005 constant. So with thermal dispersion, it's been around for a long time too. It was invented around 1914, and over the years it's become a very common technology that's used to measure building airflow measurement. Thermal dispersion, as it's used in HVAC, is typically done with two precision-matched thermistors that provide a differential temperature measurement. So one thermistor is measuring the airflow temperature in the duct, and the other sensor is heated above that temperature, and that's kept at a constant differential by applying power to the heated sensor. As air velocity increases, the heat transfer going across the heated sensor increases and requires more power to maintain that constant temperature differential. So between the applied power and the velocity in the duct, we create an algorithm, and that's an inferred measurement. It's not a direct measurement like Pitot technology. So when we look at outdoor air measurement, what are the challenges? And I think the best thing to do is look at the picture on the right. What do we see? And we don't see straight duct run. There's no duct. That's a really important concept to grasp with outdoor air measurement. Also, we have extremely low velocities. 150 feet per minute is quite common. There's gusting winds. There's a high variance of temperature, a lot of humidity changes, tons of moisture, airborne particulate, and we're often in close proximity to modulating dampers. All these things combined make it an extremely challenging airflow measurement. So when we look at the application of differential pressure, and how it can be used in OA, we realize that the big advantage is it has a ton of sensing points. That makes for an accurate measurement typically. But that technology was based upon being installed in a duct. We don't have a duct, and we need a flow profile for this to measure accurately. Also, when we get into the lower velocities, typical of outside air, Pitot technology may have some accuracy issues when it goes below 400 feet per minute. It's also because there's sensing holes that are drilled in the manifolds and the sensing arrays It's susceptible to dirt and moisture that's common in outside air. When we look at thermal dispersion, the technology seems like it's a great fit for outside air. You know, it has the capability of low air velocity measurement and to do that accurately. That's what we have in outside air, so it seems like it's a great fit. But again, that technology was intended for duct airflow mounted devices. And there's no duct on the outside air. So what do? That not having a flow profile again affects thermal dispersion. And the often forgot about portion of thermal dispersion, it's relying on heat transfer. And for that to be consistent, the coefficients have to remain constant. Heat transfer coefficients. If any contamination happens with that sensor, it's going to impact those coefficients, and you're going to lose the accuracy of the system. So now we're going to come to a third method of measuring outdoor air, and it's static differential pressure. And what we mean by this is there are fixed outdoor air inlets, and I'll show some examples of those in the coming slides. But those fixed inlets act as a flow conditioner and create a uniform static pressure field on either side of the inlet. And then that velocity can be determined by measuring the differential in that static. As you look at the governing equation, you can see that it looks very similar to our Pitot equation. You know, you'll notice that it's not a square root function though. The exponent is actually derived from the inlet type. As well as we don't see the 4005 constant that we saw previously. Again, based upon inlet type and application, it's determined. So what does that fixed inlet device look like that provides us with this pressure drop? And the typical one that we're going to see is on the left, the architectural louver. You know, a louver generates a pressure drop. You know, in some cases we might not have a louver, or we might need a different type of pressure drop, and we can accommodate that with an expanded metal. We can see in the middle there's a fabricated section of duct with expanded metal, and then on the right we actually see a rain hood that has expanded metal mounted to the bottom and a sensor measuring across that expanded metal. So most of these fixed inlet devices, especially the manufactured louvers, have an associated pressure drop curve. And what you see before you on the right is typical of a pressure drop curve for a standard louver. With this curve, we're able to set up a system that can measure this pressure drop and immediately know what the air velocity is across that louver. You know, some of the existing louver inlets, I know they can get old, might not have that data to be able to characterize it at the factory. But that characterization can be accommodated for in the field with a face velocity traverse and comparing that traverse to the differential pressure measured. So we can create that. And then lastly, if there is no louver or there's no fixed inlet to use, we can provide an expanded metal that will accommodate for that. So when we look at static differential pressure and comparing a louver or fixed inlet device, you know, with an expanded metal, you know, the question might be, well, you know, how high is the pressure drop of that expanded metal? Is it going to be undesirable? And also, am I going to generate enough differential pressure with my louver? And the first line I want to draw your attention to is the blue line, which this is for an expanded metal. It's a station. And at 600 feet per minute, we can see by the graph, well, if you can read that, it's approximately 0.15 inches of water column dP at 600 feet per minute. And it's actually at a higher dP than a typical louver is. And if we move up to where the louver's at, or sorry, it's at a lower dP than the louver, if I can read the graph correctly. I need to reverse the graph on this one. But if we go to the louver is actually at a 1/4 inch of water column. You know, expanded metals generating sufficient DP, you know, at 0.15, the louver is obviously generating sufficient DP for an accurate measurement. But what this is also telling us is that expanded metal has less pressure drop than a typical louver, you know, and it should not create or generate too much pressure drop for your system. Then we look at, you know, it's a broad measurement range. So how do you interpret these low DPs and, you know, over such a broad range with the electronics? And the key is stage transducers. So we're using 2 transducers. We're using one for the lower range, which we can see in the blue here, and we see one in the orange and red. The second transducer is going to measure in the high range. So we're wanting to keep the measurement accuracy to within plus or minus 5% of reading throughout the entire calibrated flow range. To do that, we're going to automatically switch between these 2 transducers at a transition point that's going to keep the accuracy within that measurement area of plus or minus 5% of reading. And here we can see that falls right around 400 feet per minute, where we're going to make that transition point. That ensures accuracy in the measurement system. Some of the applications out there, you know, this is probably the most common, is a single inlet. And on the left-hand side, we see a single louvered inlet for measuring the minimum and total outside air, and the damper is just downstream modulating. The sensor's been mounted across that louver that's creating the pressure drop to measure. And on the right-hand side, we see, again, a typical rain hood installation where the expanded metal's been installed. So for outside air measurement on your air handler, things can get more complicated. We can have multiple louvers, and we can have a single measurement system on those multiple louvers. But the caveat is that the area of the louver, the size of each of those individual louvers must be equal, and the dampers must operate in unison. If that's the case, then we can bring all those sensors back in parallel to a single electronics package that can interpret what the DP is and convert it to flow. We also have cases where we also have cases where we have split inlets. Yeah, updated. Okay. Sorry about that, just updating. We have cases where we have split inlets. We're measuring the min and the max. And the system is actually designed to measure both of those independently and sum them if that's what's required. So in this case, we have a smaller minimum inlet, a larger maximum inlet. Typically, that maximum inlet is associated with the economizer mode. So only the minimum damper is going to be operated for minimum outside air. When we need economizer, both open up, may operate in unison, or they may operate independently at that point. Regardless, each of those inlets is going to have a separate measurement that's going to be tied back to dedicated transducer channels on the same system. That system can actually sum those airflows together and provide the total OA output throughout the entire range of operation. And then on a similar example, we have a dual inlet. And we might have 2 ducts that are feeding 2 separate air handling units, but they're going to be measured by the same system. So each duct has its own dedicated transducer channel, but again, you know, 2 individual measurements off that one system that might be sharing the same plenum. And this is just, you know, I've talked a lot about systems, so to give everybody an idea of what it looks like, you know, the system has multiple pressure transducers. There's a reference temperature sensor and as many flow elements as we need for the application. And the sensor itself, to give everybody an idea of what it looks like, so the sensor is designed to reliably give you an accurate signal even at low airflow velocities. Finally, we talked about all the challenges with outdoor air, and what we've gone through is a system that's designed specifically to measure outdoor air. So it's accommodated all these challenges. It's been not designed for ducted airflow, but designed for outdoor air measurement. So we're looking at, what makes that true. It's impervious to moisture, dirt, debris. It's unaffected by those things. It's unaffected by rain. The fixed inlet device creates a uniform pressure field, and that eliminates the need for straight duct run. And we also have the capability with the dual transducers to measure over a broad range of flow and maintain plus or minus 5% of reading. So, in measuring the amount of outdoor air for a high-performance building, I think it's successful with the operation. It's key in assuring its successful operation. Barry went through a lot of this earlier to discuss this. If you're going to measure it accurately. I think we've presented the available technologies and tools out there for accurately measuring, outside air. And I think it's up to you to determine and define the requirements for that outside airflow measurement on the front end. So if there's that value engineering scrabble at the end of the job, it's not sacrificed. And I want to take just a couple minutes to talk about AMCA certified ratings. Air Monitor has been a proponent of AMCA for quite some time. We began certifying our flow elements back in the 1990s. And it's a great program. For those that need a little bit of an introduction, I think there's some good performance standards and publications that have been written by AMCA that would be of value for review. The first one being AMCA 600, and it defines the principles of measurement and the types of devices available. It also gives some guidelines on the location of measurements and systems and ducts. It also quantifies the effect of the installation environment on performance. It's a good publication to review, and it's going to go into more detail and depth that we could possibly do here in our 1-hour webinar. Also, you'll hear, when it comes up for AMCA certification, you'll hear about 610 and 611. 610 actually defines the laboratory testing methods to determine the performance rating of an airflow measurement system. 611 actually is the criteria for publishing certification results and performing the periodic retesting that's required to keep up the AMCA certification of those products. So why talk about all this? I mean, we certainly feel there's value in third-party performance verification. I think that there's value for the end user, customers. I think there's value for the manufacturers in AMCA certification. It keeps everybody on the same playing field. It ensures that the manufacturer's claims, their published performance specifications, are achievable in the field. And that third-party certification, if you have two products that are both AMCA, it's going to be an apples-to-apples comparison, that you'll know that both of those can achieve those performance claims. Air Monitor, to ensure that we're meeting our performance claims, we actually developed our own test lab. The reference device is 4 12-inch ASME flow nozzles, pretty widely accepted as a very accurate flow reference. And that's combined with a 100 horsepower, 36,000 CFM capable fan. And what we can do is we can do full-scale airflow testing of virtually any configuration we want. This helps us with research and development. It helps with demonstration of product, with training, and with manufacturing quality control, because we can bring our products back in and ensure accurate measurement. That brings us to our question session.
Yeah. Good.
So yeah, at this point, thanks, Matt. At this point, we're ready to start reviewing questions and answers. I want to thank everybody for attending the webinar, and we'll try and do our best to answer the questions that are thrown our way. As I said, anything that we don't get to during the live portion, we will certainly provide an email answer in relatively short order. So without that, we're going to start reviewing some of these questions and see what we can come up with. I'll come in.
Yeah, the first question. Yeah, our first question we've got is, can the system interface with BACnet or via BACnet to the BAS? And the answer is yes. It is BACnet ready as well as Modbus.
So the next question, what specifically makes this product impervious to changes in wind velocity and direction? So there are a couple things in our favor in terms of wind direction and velocity and wind gust. Basically, the sensing element itself has to be designed so that the upstream static port is protected from seeing wind velocity. The downstream portion of our sensing system, or the static pressure sensing on the opposite side, is just that. It's just measuring static pressure as it moves across the air device or the fixed inlet device. So what we're not seeing is any velocity pressure. In other words, our system is not affected by the velocity pressure itself. We have to see a static pressure drop associated with the air moving across that inlet. And the velocity has to be consistent enough for us to actually ascertain that differential pressure measurement. So I think that the key for us is that it's not a velocity pressure measurement that we're looking at. So the gusting winds and those types of things, it needs to be developed so that there's a static pressure difference as it moves through the inlet. I guess we should say who's answering this. Matt, you want to?
Okay, so the next question is, how often does a thermal dispersion flow station require cleaning or maintenance? For our system, it's really going to be application dependent. How much particulate contamination, how much moisture, how much buildup do you have on the sensors? I can say that thermal dispersion flow measurement devices are extremely sensitive to any contamination at all. So if there is relatively high dust loading, or there's particulate or moisture in there, they're going to have to be cleaned very often in an outside air application. Do you want me to get that one? I can take it.
Which one's the turn down one? Okay, another question that came in is, please explain turn down ratio again. This is Barry, and turn down ratio is as simply put as possible, it's the maximum achievable flow rate of the instrument divided by the minimum, more or less, achievable flow rate of the instrument. So most instruments have an accuracy based on a certain flow rate range, and that flow rate range will work from a minimum all the way throughout a maximum flow rate. So in determining the turn down, the first step is what's the maximum flow rate, divide that by the minimum set point, and you have the overall operating turn down of the device. The important slide for us, or discussion point, is the effective turn down. And that's where we look at the actual maximum operating range of the device divided by the minimum. Because the minimum, just because the maximum may be reduced, the minimum set point remains constant. So that's where it really becomes important to kind of compare apples to apples on differential pressure, or I'm sorry, on the turn down situation that we're looking at, are we looking at the total instrument turn down or the turn down as it will actively or actually be applied to the system?
Okay, I'm actually going to combine together a couple questions to answer here. And the first one is, your example showed a quarter-inch pressure drop across a louver at 600 feet per minute velocity. This seems to be much higher delta P than most louvers we see. And then the second question I'm going to combine together with this is, what is the minimum differential pressure that a measuring device can be applied to, or pressure drop, sorry, that the measuring device can be applied to? As far as the first question goes, it might be high for a louver. Of course, we can take louvers that have much less pressure drop than that. The quarter inch, if you have a louver that's more intended for rain, to prevent rain from coming in, it's going to have a higher pressure drop. That's a reality. When we talk about what is the minimum pressure drop that the device can measure, we're at least at 0.003 inches of water column, so we can measure a very low pressure drop with this device. So the next question is, when calibrating a louver, what field technique do you recommend? It really depends on the application, what's available. Obviously, there's probably not going to be any ductwork where it can do a standard field traverse. But what we would recommend is a face velocity traverse. So right in front of the louver, we split it into equal areas, take a measurement in the center of each of those equal areas, average it, and figure out what the average velocity is across that louver. So one of the claims to fame of a major competitor is that it remains accurate for many years before needing recalibration. How often does the static differential pressure system require recalibration? So for our system, the critical calibration point is the 0 point. And the system actually has an auto zero function. So it periodically zeroes the system. So there's no need to ever calibrate 0. As far as the span or the maximum differential pressure for the system, it would be recommended to repeat the calibration about every 3 years.
Yes. You want to take that? We have another question about the mesh involved, contamination from poplar fluff.
Yeah,
which is an interesting
dilemma
with outdoor air in general.
Absolutely, Barry. I think, and I'll read the whole thing here. It says, using a mesh would involve contamination from poplar fluff, etc., and would require cleaning on a regular basis. It would also provide erroneous readings when it is contaminated. I think, in that case, I'm not sure if it's a rain hood or if there's no louver available. If there's a louver, obviously the louver can be used. But in most outside air applications, especially when you have this type of seasonal contamination, you also have bird screen on these inlets. And that bird screen will end up getting contaminated too. So I don't think we're inducing any additional maintenance beyond what's already going to be required for that type of regional and seasonal contamination. But it's not going to affect the accuracy or the performance measurement of the system.
Okay, I'll take another question that came in and says, it asks, do you use louver total area or free area? And the answer is the relation that we use in determining the flow rate range is based on face area of the louver, and or the inlet. And there's a reason for that. In most cases, we are always looking at total CFM in terms of the opening itself as it comes through. Louvers themselves have published free area, some louvers do, but in many installations there is not a published correlation between that free area of the louver to the face area. It's also something that when we're trying to determine the best geometry to use in terms of where sensors are placed, we want to look at the total face area, or the total areas in this case, rather than the free area, and stick with something that is known. So, and generally speaking, the louver, the free area, what that means in terms of design is there's a velocity that's used, kind of a worst case velocity for carryover. For us, we want to compare the velocities to that face area so that we know what the CFM readings are across that range. We're not really interested in trying to figure out what the actual velocity is on either side of the static pressure device in terms of what our equations and metrics are. So. Okay.
The next question is, what is the sensor resistance to corrosion considering various environmental conditions, including coastal salt air? And what I can tell you about the sensor is it's manufactured out of 316 stainless steel. So for the majority of applications, there's no issue with corrosion whatsoever. So the next question, what is your oldest installation? How long have you been installing this product? So the OEM first hit the market in, I believe, 1997. So we're coming up on, well, it's the 20-year anniversary of the product. And we've been installing the product for that long. Now the product, has been iterated, and we're on the OAM 2 now, which, added features like a better display and network protocols and communications, and improve the overall performance of the processor.
So another question that just received discusses how many sensors basically. Do we need multiple sensors based on the area? Do large louvers require multiple sensors? And the answer is yes. There is a more or less a design guideline in terms of 30 square feet per sensing point. But again, one of the points that Matt brought up is when we're looking at big louvers, we need to make sure that all sections of the louver are controlled together. And that the louver is the same louver in terms of its characteristics across that range. But in most cases they are, and when you have a large area or large louver encompassing a large area, it's not uncommon to manifold 3 or 4 sensors together and bring those back to a single system or to a single transmitter.
The next question is, do I need to include auxiliary temperature sensors to accommodate or compensate for the outside air temperature extremes and calculate separately? The answer is no. You don't need that. That's included as part of the OAM system. And it's calculated, the density compensation is performed automatically, and the flow output is accurate and accurately density compensated output.
So there is a next question is, what are the inlet and outlet duct straight run requirements for the static DP sensor compared to other devices? And the answer is, as we've been talking about all throughout the presentation, is It really depends on the inlet. If it's an inlet that we have characterized information on, which assumes some type of mesh or a station or a louver, the answer is none. We don't require anything upstream of that device. If we are going to be mounted inside a duct with a station, and we're looking at the pressure drop across that, there are some things, some straight run issues that we may want to address at that time. But for most intents and purposes, zero straight run is required for this technology, provided that the airflow is going to be conditioned properly, and we'll be able to look at that generated static pressure field on either side. So that's one of the benefits of this device, and it's something that can be utilized in a number of other areas, but as Matt indicated, it's a device that's specifically designed for outdoor air measurement across fixed inlets and louvers and those types of things.
And to add just a little bit to what Barry is saying, how about the other devices? Those other devices, for that upstream requirement of a louver, when we're talking about thermal dispersion or Pitot technologies, those will typically require 1 to 5 duct diameters of total upstream and downstream straight run, including distance upstream of the damper to measure accurately within their performance specifications. Okay, so the next question is, the dual transducers that are on board the system, are you able to field calibrate, zero and span by your own technician, I assume in the field? And with the proper tools, absolutely. We're dealing with very low differential pressure, so we have to make sure that you have a capable digital manometer to perform that. I can say with the zero calibration, I mentioned Auto Zero previously, and Auto Zero takes care of the zero calibration, at least once a day. And the next question is, do you foresee a problem with verifying airflow at another location, such as the cooling coil? This considers the units running on 100% outside air during the testing. I think that might be acceptable. It really depends on, how are you trying to perform that measurement? Right downstream of the cooling coil, right upstream. What are the other conditions in that location? Obviously, you're going to be doing traverse testing for that verification. So some of it also has to do with methodology. But I think that, if a field technician has good experience and understanding and he believes that's a good, accurate measurement location is available in that area, then yes, you can verify airflow in that location. I think it might be a challenge because there might not be enough straight run for the technician to actually even get a good measurement there too. But if it's available and the technician thinks it's okay, absolutely use that.
Okay, another question basically along the same lines just has to deal with, is it beneficial to compare a calibration flow at both the design maximum and minimum airflows? So we have to, really we have to worry about the term calibration. So the device can be calibrated at the factory provided the conditions are known at that time. But in the field, what we're doing is more or less a field commissioning or a field validation. And in our experience, if you can achieve, that maximum and minimum design, the unit will allow you to put those values in so that you can have a very accurate measurement across that entire flow point. But again, that's based on something that's not meeting a calibration point for the meter. In other words, there's some type of inlet device that does not have either published pressure drop information or it doesn't match the additional curve. If the meter is calibrated against a factory standard, which is the recommended way to go, we definitely recommend for a field validation. In other words, use the measurements that you see in the field from the instrument and use those as commissioning and as the basis for comparing, but we don't recommend recalibrating a factory calibrated device, because the field, the field devices won't generally be as accurate. It really only comes into play, again, if it's something that was not able to be fully characterized at the factory. So that is a great question, something that we deal with quite a bit.
I think we're almost running out of time, but I think we have time for a couple more questions. One more question. Okay, the question is, are there specific louver types that this product cannot be attached to? Minimum blade spacing requirements. And really, the minimum blade spacing requirements are approximately 1/4 to 3/8 of an inch. So we really don't need a lot of spacing. It's just for, the sensor to fit through and get to the other side of the louvers. We have not encountered a specific louver that we cannot apply the technology to, but it's always possible that there are some louvers out there that might be more of a challenge. If that's the case, we can introduce what we call our OAM station that'll have the expanded metal and provide you with an adequate pressure drop that we can measure there.
Okay, we have time for about one more question.
One more?
Yeah, before we get booted out of here. But this is, Matt, do you want to?
Okay, and the next question, or the last question, how difficult is it to install the probe in a bird screen on a typical RTU? Not very difficult at all. You need access to the outside of the bird screen. We're talking about installing probably 3 or 4 screws, and then tubing from the sensor, which is going to be on the outside of the bird screen, facing the sensor, and then that goes back to the electronics panel.
And that is provided that the bird screen will give us the
pressure drop required. If it doesn't, it can be replaced with a piece of expanded metal.
Well, we're about out of time. Really want to thank everyone for the time today, the questions. They're great. And as we said, there are a number of questions I know we haven't gotten to yet. The list is in front of us, and we will be working diligently to get those answered and emailed out to everybody. So
thank you all for attending today.